Welcome everyone. Here's a lecture on event processing, which will be one of the two lectures on control signal processing. And all this in the context of generative music and potentially music interfaces, instruments, quite a lot of things really. The point about control signal processing is that it is pretty much deriving the techniques from audio signal processing. At least the interesting things are mostly derived from audio signal processing, which will potentially make those even more clear because we get to see these processes at a slower rate. So the key to control signals is that they are running at slower rate. So similar to audio, obviously it is a stream of data, stream of numbers coming in. And they typically come in from different sources, like user interfaces, dials, sensors, or indeed they can be derived from music. Typically you can consider a MIDI data stream also a control signal stream. So the thing to understand at this stage, which is crucial, is that the audio signal processing relates or depends on a fixed sample rate. So most of those things like filtering and many others will depend on a fixed sample rate, and with control signals we may or may not have a fixed sample rate. So typically if you have a dial, a slider, it will send out values only when the value has changed. So the rate, the timing between these values will not be fixed, which means we don't have a fixed sample rate. So you will see very frequently when we do apply these techniques, we will impose a fixed sample rate. We will sort of resample the signal. Okay, so in some audio environments you will have a fixed control rate, which will typically process one sample per audio buffer. Could be 512, depends on the setting. In Max MSP, which will be the platform to show you some of these techniques, there is no such thing. You essentially have messages that can run at a fixed rate or audio. Now, the basic thing that we do with control signals is we distinguish between events and motions. Okay, so it kind of has to do with fixed sample rate and not fixed sample rate, although it is not a clear map, because we can create a fixed sample rate for an event stream, in which case typically one event will be reported as ongoing while it's happening, and we can actually describe a motion at variable sample rate. Could be meaningful, but conceptually, so the technical distinction is fixed sample rate or not, but the conceptual distinction is crucial here, because what we will look at is a various set of ways to transform events and create a continuous description of these events. And then we will also look at motions and look at extracting events from these. So and obviously there will be techniques to kind of transform the events, analyze them, and get an output, which is also an event-based signal. And similarly, motions will be analyzed to gain further continuous signals. But the very interesting thing is typically going from one to the other and back. Now, in terms of control signal processing, typically you would have two approaches. So one approach is kind of conceptual, meaning that you have an idea in terms of what do you want to get out of your signal processing. So you have a concept. We will look at some concepts later in terms of density analysis and other things, energy, such things. But the interesting thing really is when you have a set of control signal processing tools and then use them creatively. So you don't really need to build a concept before you get into the arrangement, the kind of the tuning of control signal processing algorithms. But you can indeed say, well, actually I have a motion from a sensor and I want to get some kind of events from this. And then just get going with a range of things. So that's typically the plan for today. Today we're gonna do events analysis. And in the context of generative music, typically these will be MIDI notes. Useful distinction is between events that are just an event without any description. In Max MSP, those are bangs or triggers. So we just have an instance in time when something occurs, and then it's down to interpreting it, making it meaningful. And events can also have descriptive parameters. So typically with MIDI notes, they will have pitch, velocity, and there could be other things as well. Okay, so crucially, we're gonna look at two things and talk about a third one because it's slightly more complex to implement in Max MSP. And we don't really have the time for that, but it will be useful to understand. So first I'm gonna just talk briefly about these three. There could be more. These are the kind of basic interesting things in terms of transforming event streams into continuous data that has some descriptive property value in terms of what is this event stream like. So the first thing we're looking at is the energy, which is typically a sense of, I mean, these are descriptive terms at this stage. In terms of signal energy, maybe worth mentioning is that typically it is related to what we call RMS in audio signal analysis, which is root mean square, which is a way of, first of all, rectifying the signal with squaring just to get all positive values, then taking the mean of a certain amount of values and then taking the square root back again. So you're kind of figuring out what is the excursion, right? The excursion is the amplitude of the signal, but we're figuring it out over a larger time span. Now from physics, the way they approach energy is that they look at the area underneath a curve. So typically this is what is proportional to the amount of energy of an amplitude signal. Now we won't really, I mean that's the essentially the integral of the signal, but and actually it does come in here. It is related because an integrator is essentially a low pass filter. In order to integrate a signal, essentially what you do is you add up values one after the other, and then if the signal is bipolar, it would typically zero out over time because you add up negative values into it as well. But if it's a unipolar signal, you essentially get an explosion of this low pass filter. Unless there is some kind of compensation. So typically we have, for this, we have something that is called a leaky integrator, which kind of leaks out some energy. So you can use it with a unipolar signal. I'm mentioning these things as a matter of interest You can look these things up. I reckon, obviously, I have to choose my battles here, and I'm trying to keep it quite practical. So, all in all, for us, a low-pass filter of a time function is something that will come close to the estimation of energy. Now, the thing is that we are purely practical in this case, and therefore, we are free to come up with a variety of different ways to come close to what we call the estimation of how much energy there is in the control signal. And in order to make this simple, maybe the best thing is to just consider a stream of MIDI notes, because in that way we can relate to the energy of a performer, right? So if a stream of MIDI notes comes from a piano, we would all be able to estimate how much energy is the piano player actually investing. So in a sense, we could be extracting this energy, by the way, from the audio signal as well, right? That would account for many things. However, if you think about it carefully, what does the energy of a piano player really entail? Well, first of all, energy is sweat. How much does he have to sweat? So typically, very loud notes will demand more energy and come over as more energetic. So what we can do then is typically look at the occurrence of notes, right? Because if the piano player has to play more notes, then he has to exert more energy. And then if he has to play loud notes, that's more energy as well. And if he has simultaneous notes rather than single notes, that's more energy as well. Typically, a piano player doesn't really have to exert energy for holding the notes. But again, we're not really analyzing a piano player right here. We're just looking at things that relate to the sense of energy in a stream of MIDI notes. So the first thing will be is to take a low-pass filter of a time function, so the incoming notes. Obviously, you could think of cases when the pitch of this note might contribute to the sense of energy. I mean, typically, if you play a tuba, a low note really takes much more out of your lungs compared to a high note. And then obviously with the velocity, we can relate that. So typically what we're looking at here is kind of combining different things. And then density as well, but we will look at this separately because it's a different technique, right? So in terms of energy, we're looking at low-pass filtering the signal, so we'll look at that. In terms of density, we're looking at the reciprocal of entry delay times. So we're looking at how much time there has been since the previous event. And the reciprocal means 1 over that value. So the shorter the time between successive events, the higher the density. Okay. And then you will see how low-pass filtering is useful here as well, because it is a signal smoothing process. Okay, so those two we will look at in some detail with some patches. But before we go there, I'll just introduce another concept from audio signal processing that is transferable to control signals, which is the bandwidth. And in control signals, this comes down to regularity. So just as in audio signals, when you have a fixed frequency, a sine wave is the narrowest possible bandwidth in audio signals, and it is extremely regular, right? It's actually periodic. Now, if you jitter the frequency of the sine wave, if the frequency of the sine wave moves up and down a bit, then what you will get is that the bandwidth widens. So if the bandwidth widens, what we can say is that the signal becomes less regular. So in a similar way, if you have a control signal, let's say you have a set of MIDI notes coming from a drummer, then you can actually estimate the precision that the drummer plays with by looking at the bandwidth of this signal. So here's an example. If you try to produce events at 120 beats per minute, that is 2 hertz, right? So what that means is that if you run your spectral analysis at those low rates and you have a very precise pulsation at 120 BPM, you will get a very narrow peak at 2 hertz. So the reason why this is not an easy technique to implement is that FFT, which is our spectral analysis, typically does not allow to go to those low frequencies, depending on the implementation. You could work around this. In Max MSP, probably best would be to just enter control signal values into an audio buffer, and then get the FFT of that audio buffer. So it could be tricky. I mean, in Super Collider it should be slightly easier. Some other, obviously if you're the lower level of coding that you employ, the easier it could be. But another potentially simpler way of doing this, of estimating the bandwidth of a control signal, could be a filter bank. So it really depends on the implementation of the filters on the platform you're using. But there is no reason why a bandpass filter could not be set at 2 Hz in between other two bandpass filter at 1.5 Hz and 2.5 Hz. And then you essentially have a filter bank, and then you can use amplitude estimation, RMS estimation on those different filters in the bank and figure out the difference between the peaking one and the ones on the side, and you could kind of get an estimation of the regularity. So all in all, we're looking at the energy of control signals and the density of control signals, events, I should say, although these would translate to motion as well, density less so, but energy definitely. And then this brief introduction on how regularity also relates to audio signal processing. Okay, so let us then look at these patches. So the first thing I've got here is a low pass filter at control rate. So I have a fixed sample rate, which is 100 milliseconds. So I have 10 samples per second. And then at that sample rate, I'm creating a random signal using the trunk, which will allow me also to create a different pace, as I typically call it in the moving random value. So we can immediately look at this, or we're looking at the top window here. So currently my drunk has a range 0 to 100, which is the range of this table. And then I have maximum step size of 16. So the next step is 16 values away from the previous one at most. Now, if I increase the maximum step size here, what I will get is a more erratic random signal. So I'm nearing white noise. So now pretty much every sample is totally independent of the previous one, except what you can notice is my maximum step size is so large that a lot of values would want to go beyond the limit 100, but this implementation is such that they're just capped at 100. So what you get is that if you create too large of a step size compared to the range, most of these values stick up there. And then if I have a fairly small step size, then what I get is a signal that kind of slowly moves up and down and creates a more easy to appreciate random curve. Okay, so we're looking at what does low-pass filtering do, and what it does, it smooths out this signal. That's what essentially happens here. So this is an infinite impulse response low-pass filter implementation, and essentially what's happening here is that the number is coming in from the noise, and to that number is added the previous value, which was multiplied by 0.98. So that's all that happens. I'm adding to the current input value, I'm adding the previous output value times 0.98. Actually here we're looking at smoothing with 0.815. This DFB is here in order to make sure that these things happen in time. So when it receives a trigger, it will first bang, then it will send out the floating point number, and then the bang is here in order to get the previous output value. So when an output value comes out, then it is multiplied and stored in the message box, but it is not output at that point. So the message box serves as a memory cell which gets the previous output value, and when I have to use it, which is on the next input value, first thing I bang that, I get the previous output value, then I get the current input value. These two added become the next output value, which comes out here, and then that's stored back again for the next cycle. So it's fairly simple actually. So just multiplying the previous output value with a number and adding that to the current value. And this is what we get. So what I have here is a scaling, because what happens with this filter is that it goes, it doesn't scale together with the original signal. I mean, this is the simplest implementation possible. You could make a filter which actually follows the range of the input signal. Although typically when you filter out high frequencies, you lose some energy in the signal. So I have a manual scaling here just to make sure. And then what you see here is that this signal, this is the filtered version of this noise signal here, is essentially the same thing. It has the same peaks and troughs, but it's a bit smoother. So already you could imagine how this could be useful, for example, in control signal processing. If you have some sensor signals which are quite erratic, if you have a fader and you want to smooth it out, many things. And obviously in terms of combining signal processing, control signal processing, it can be really useful as a tool, because you derive signals, you process them, and sometimes you just want to have them smoother. So that's what's going on here. And then this coefficient, this multiplier, is the crucial element that controls the filtering characteristic. So if I push this closer to 1, well, first of all, you see my scaling has gone up, so I'm gonna have to pull that down a bit. Can I get there? Can I get there? Oh, I've missed it. 0. Yeah, here is something. So you see, I'm still having a signal, but it's actually it's really smooth. Right, so I'm just getting a very small variation here. So you see, it kind of has dropped. Now kind of gone up. So it is really, really smoothing it. So if I want something useful, probably need to go down a bit further here. Okay, 0.9. That should be fun, more fun. Okay, so here I have a already usable thing. It kind of looks like the input signal. And then if I have something really low, then I will get even less smoothing. Again, I'll have to play with my scale to get these in line. It's a bit too much. Okay, and then the interesting thing is that this is an infinite impulse response scheme, which can also act as a high-pass filter. So in control signal processing, the high-pass filter will essentially remove the overall offset. So it will remove the slow motions and it will retain the fast ones. And I achieve that by creating a negative coefficient here. Let's see how far I can go, still keep this fairly stable. Okay, so what I'm essentially gone too far. Uh-oh, it's blowing up. So what you just see is a blowing up infinite impulse response filter, which is something that can happen because of the feedback loop. So I have a little reset 0 here. So it seems like I have some high pass filtering going on here. And what I expect to see then is I expect to see peaks when there is a lot of signal change here. So while the signal is fairly slow, kind of slowly moving, I should get fairly stable signal here, and when there is a jump, I should get a jump. But the overall offset of the signal should be reduced. So these big motions should come through less, and what you get is these small little jumps. And the reason is obviously because what we're doing is we're taking the difference essentially of the previous value to the current value. So it's a kind of a differentiation. Again, it is not accurate in terms of maths, but in terms of designing control signal processing, it can be quite useful. So the last thing to look at here potentially is when I increase the erraticness of this noise signal. You see that comes through really neatly in terms of that being more high frequency energy. But if I have a fairly slow signal there, you see how it's actually damping the slow movements and kind of keeping the big ones, keeping the short erratic movements. Okay, so that's infinite impulse response filter in control domain. Obviously it's the simple version. There is no multiplier for the original input value, which would make things a bit more complex and a bit more flexible. But essentially we're just looking at these basic techniques here. Okay, so from here I have a little patch that estimates the energy of a signal. And what we do here is we take a fixed sample rate, 10 times per second. We take a random value up to 300, step size 80, and with that we are essentially creating random time intervals. Okay, so in this case, if this goes up to 300 plus 100, that means that every next time interval will be between 100 and 400 milliseconds. So I'm kind of self-modulating the metronome here. The metronome, every time it creates a trigger, with that trigger it computes its time before the next trigger and feeds it back here. And then I can control the range and the offset, and thereby control the actual set of values that this metronome will take. Now every time it triggers, so we know now it's triggering kind of randomly in a given range. Each time it triggers, I create a random value up to 13. I times it by 3 and add 50, and this becomes the pitch of the note. So what happens here then is that I get a set of values, well 13, every value up to 13, actually it's 0 to 12 times 3 will give me 0, 3, 6, 9 and so on. So I have a given spacing between these notes, and I add 50, so the set of values I end up with is 50, 53, 56, 59, 62, 65 and so on. So I get some spacing between MIDI notes, so they are not chromatical. And then I have a drunk with somewhat smaller step size than the range. Again, I'm multiplying by 4, so I get a spacing between the values. So you can also do the math here. The maximum value is 31 times 4 is 124. Minimum is 0 times 4 is 0. So actually I get values between 0 and 124. And that becomes the velocity of my note. Okay, so I get a kind of a thing. You can see the random time intervals right here. I'm not displaying the pitches, but you can have a look at those as well. These are the pitches, MIDI notes, and these are the velocities. Okay. Now, because I have a drunk, you see, for my timing, what I can do here is I can have sections where stuff speeds up and slows down and kind of stays fast and stays slow. So it's not a uniform random output. So it's not equally likely that the note will be fast after the next one or slow after it. But it's actually gonna stick in different speed ranges. So if I play a few fast notes, they will stay fast, which is potentially musical. I'm kind of doing and then obviously I can change the range of this playback. So my offset is currently 100. I can make that less. Oops. I can make the overall range smaller, or indeed I can make this much slower. Okay. Cool. So that's my generative mechanism to create these piano notes. And well, actually what I think I can do as well, if I control the pace for the velocity randomizer, I can make them go slightly, kind of keep to the same dynamic for longer, make it a bit faster so we hear this happening. So now velocities are around 100 and they stick there. And if they become slower, let's give it a bit more range. And if they become softer, ever, then they're bound to stick there and stay soft a bit. See? Now they're kind of medium velocity. Now in this case, obviously I have 3 random generators. One is responsible for the timing randomization, one is responsible for the velocities, and one is responsible for the pitches. But an interesting thing would be to actually derive different values from 2 randomizers maybe, such that you can use one to contribute to pitch and velocity, another one to contribute to timing and pitch. So kind of make these things relate. It will create a more musical motion. But I'll leave that to your own experimentation. So what we're looking at here now is my estimation of energy. So what I'm doing is I'm taking the velocity of notes, dividing by 127. So I get into the range of 0 to almost 1. And then what I'm doing is I'm resampling the signal. So I have a metronome at 2 milliseconds, so 500 samples per second, which is obviously much faster than the density of the notes. And then every incoming note is being kept in the message box and triggered out this many times per second. So what I expect to get here then is this is the output of my resampling. So these are the notes one after the other. But here, because it's a higher sampling rate, I actually get multiple samples outputting the same value. So this is a fixed sample rate. So the time flow is constant. You see this one moves faster when the notes are faster, but this one moves with a fixed speed. So that's my resampling. I'm imposing a fixed sample rate there. And then what I do is what you've seen a second ago. So I have this feedback loop with a low pass filter in there. And then what I get is a curve that derives from these values. Again, I have manual scaling because this is a rather simple thing. And then this curve already should give me some sense of the energy in the signal. Okay, so this one is strictly informed by the velocity, and obviously you could use a density estimation and make that contribute as well. So that will be our final thing. Let's look briefly at the density. So what I have here is the same timing randomizer, and I have a very similar music engine to create pitches and velocities at random. And you see, actually what I'm using for my density estimation is just the triggers themselves. So I'm not using any values, just the banks. So in order to get there, what I do is I have a timer which will essentially calculate the time. I can check it that they correspond to these values. And what you will find is that there is an offset. This one comes later than this value. So next one up. Oh, well, this one took a while. So you see, actually, the previous note now lasted 10 seconds because I've stopped the metronome. So if I keep it running, you can see that these are the same values. This one just comes one later. And I'm doing this because I want this density estimation to be applicable in multiple situations from live input as well. So I'm not relying on knowing the time interval, but I'm calculating it here. Okay, so once I have the time between triggers, I take the reciprocal value, so 1 over. So in max MSP, exclamation division is essentially swapping the places of things you divide. So I can briefly demonstrate that. This will be 1 over the input value. So 1 over 49 is 0.2, and then if I take 0.02, oops, point, well, that's actually 50. It was truncated. So that's the reciprocal value. So the smaller the value as it nears 0, it will be higher. The reciprocal is higher. 1/1 is typically 1. And then if I increase this value, then I'm nearing 0 here. So that will be something that relates to the density of events. So let's see that. Here it's playing. And then when my piano speeds up, I see these values speed up as well. Okay, I'm doing some scaling in between just to get a good range. And that seems to work nicely. And then what I do is I resample this signal. So similar to the previous example, what I then get, let's put these values, is a constant time flow, same values. So in order to make a meaningful signal processing appropriation, I really need to do this. And then, just like previously, I use a low-pass filter to smooth out these values. So this would typically be a curve that, see, there it's sped up, increasing density. And it's actually still fairly detailed, but also fairly smooth, which can be quite useful, obviously, if you try to use this as a signal to control any other parameter. Okay, so those were the basic things there. And then we will look at exploring these techniques and kind of getting friendly with them in some exercises to follow. Thanks for your attention.